The ASC conference is always a highlight for us at PSN, and it's a real disappointment that we cannot meet this year. Nevertheless, it's good to be able to keep in touch by email, Microsoft Teams and Zoom, and to know that you're keeping safe. The GenStat team is dispersed over 2 hemispheres, and so we're used to working at a distance. GenStat development has continued almost unaffected, and I'm glad to have this opportunity to tell you what we've been doing. We're developing GenStat-based apps for future cloud services, which we shall be able to demonstrate when we can next meet together. The main activity, though, has been to complete the 21st edition of GenStat. The 21st edition of GenStat was produced during 2020 and released in December. There are many new features, which I've shown on this slide, but if you're within GenStat, you can see them within the help by opening the help and then clicking through on the item Find out what's new in the 21st edition. So as you can see, there are quite a few new menus as well as smaller enhancements. And if you want to see what's new in the server, you can click through on the release 21.1 highlight there, and you can see we've got 2 new directives, 19 new procedures, all listed down here, as well as a whole range of other smaller updates. So I recommend that you have a look at those when you get hold of your copy of the 21st edition and see what we have there to help you improve the way in which you do your analyses. Well, I'm going to start by looking at analysis of variance, which is my own area, of course. I've got a new procedure, ABLUPS, which will calculate best linear unbiased predictors for block terms in generally balanced designs. Previously, you could only get these from REML. So this is the one aspect of the output for generally balanced designs that ANOVA wasn't able to provide, that REML could provide. This shows it in action. Let's do that within GenStat itself. So I've got the split plot design variety trial of oats that I'm sure you all know. If I open the analysis of variance menu, I can analyze it. But first of all, let's look at the options. So you can see in options, we now have a checkbox to get the BLUPs. I'll only do the analysis of variance table and the BLUPs so that you can see these when we do the analysis. So click on Run, and you can see here we have the ANOVA table and indeed the BLUPs for the block terms. So that's the enhancement in ANOVA. Next, let's look at design. And David Baird has implemented a very nice algorithm to generate doubly resolvable row-column designs. And that's implemented in the directive AGRC resolvable, that has the algorithm. And then there's a procedure, AFRC resolvable, that calls the directive and puts together the output in a more comprehensive way. So this shows a run of the procedure. You can see we've called it through the menu, but here's the script that's been generated by the menu. You can see it's called AFRC resolvable. And we've asked for a design with 10 rows, 6 columns, and there are 15 treatments. The plot factor is numbered from top left, row by row. We haven't printed it here, but that's available. You can also do it from the bottom left, bottom right, and so on, and in a serpentine way if you prefer, column by column or row by row. In the options menu, we've asked to see the design in the output and also in a plot. Here you can see in the output, these are the treatments in the various rows and columns. The graph is nicer because you can see the resolvable aspects of it. In red, we've got the reps identified for the columns. Here's the first rep, here's the second, here's the third, and here's the fourth. And blue does the rows, so you can see here's the first rep by rows, here's the second, here's the third, and here's the fourth. The other new facility within design is that I have a procedure CDN augmented design that forms augmented block designs. And by augmented, we mean that we form a block design for the controls, and then we augment it by expanding the plots where we have the controls to give additional subplots for the treatments that we're interested in. So this will call site design to form an incomplete block design for the controls to do that efficiently. Or if it was just a randomized block design, of course, GenStat would do it itself. And then it augments it with the test treatments. And this has been written for the EU project EPPN 2020. That's the European Plant Phenotyping Network 2020. Next, we'll look at graphics. And Vanessa Cave has written a procedure deseparation plot. And we have a menu to call this. On the slide, we show it in action, but I'll go to GenStat and just show you how you might use it in practice. The dataset we're going to look at is one that's analysed in section 3.4 of the regression guide, and this comes from David Finney's book, Probit Analysis, the 3rd edition, and it's comparing the effectiveness of 3 analgesic drugs to a standard drug, morphine. We've got 14 groups of mice tested for response to the drugs at a range of doses. So here's the spreadsheet with the data. This just shows you how we'd analyse it through the probit analysis menu. You can see we've got the number of subjects N, number responding R, dose is the explanatory variate, but we're going to take log space 10, and groups drug. In the options, I've said, because I've analysed this before, I don't want to estimate different slopes for the groups. In previous analyses of this set of data, I can see that's not something that's necessary. So I can click on Run to run the analysis, and then in order to use the separation plot, I need to get the estimated probabilities from the model that we've fitted. So I can go to Save, and I can save the fitted values in a variant that I'm calling fitted R. And then I can use the calculations menu to get the estimated probabilities by dividing that by the total number at each dose. So you can see I've got a variant estprob which contains the estimated probabilities. So if I want to do the separation plot, I need to open the appropriate menu. You can see I put the probabilities to plot in the first box, that's estprob that I calculated. Here I've got binomial data, numbers of successes and trials, and the number of successes is R in the original data, and the number of trials is N. In the options, you can see that I can display the separation plot in a variety of ways. I'm going to use just the default displaying lines. I'll show you then how this looks. So here's the separation plot. What we have here is the star is the point at which we go from predicting failures to predicting successes. We've got the lines here showing the failures in red and the greens showing the successes. I think what you can see is that the analysis, despite the fact that you can see it's really a very reasonable fit, still isn't brilliant at predicting successes and failures, and that's basically the variability that you find in binomial data. Next, I'm going to look at the new menu that we have for response services. We've a new menu based on a new procedure that David's written, vSurface, that will fit a 2D spline surface by Remel. This shows it in use, but I'll show it live in GenStat in a moment. But just to say, there was already a procedure R-quadratic that fitted a quadratic response surface using regression. The Remel one clearly is going to be more sophisticated and to be able to fit rather more challenging surfaces. In the 20th edition, of course, we didn't have the menu, we just had the procedure. So let's look at this live within GenStat. I'm going to use the artificial data that's in the vSurface example, which I've loaded here, so I can run that. And you can see we now have the data generated that we're going to use. And I need to open the response surface menu, which is part of the regression item. You can see here it is. And I've got it filled in already. The Y variant is called Y. We've got X variant 1 called X1, X variant 2 called X2. And I'm going to have prediction levels at 1 through to 9 on both X1 and X2. It might make more sense if you were doing this in reality to have a rather finer grid, but I want this to run fairly quickly. So you can see I've selected the spline model here rather than the quadratic, which we had available in the 20th edition. In the options, I'm going to cut back on the Remel. I'll just print the variance components, the effects and the extreme point, and I will do a surface plot. I click Run. You can see it all happens, and the procedure will estimate the maximum fitted value within the grid that we're looking at. Now, the quadratic one, by regression, will extrapolate out of the area, but of course the Remel one can't do that. So if the maximum occurs within the grid, that's fine. If not, you'll find that the maximum occurs on the edge, and you might need to change your grid and fit another spline surface until you do finally hone in on the maximum. Right, next we're going to look at new facilities in meta-analysis. In medical work, meta-analysis usually means the process of producing a combined estimate of the effectiveness, say, of a new drug versus control, based upon published work where all you have available is an estimate of the contrast and its standard error. In GenStat Remel, we usually prefer you to do the combined analysis using the data from all your trials, thereby use the complete information. But we do know that sometimes this can be challenging because you may have many variance parameters to estimate, and Remel may find that a bit of a struggle. In the 21st edition, we have a new procedure, vMeta, written by Vanessa, based upon a paper by Madden, Pifo and Paul in phytopathology, which does what they call network meta-analysis, where you use the means from the individual trials, so in other words, more than just the one contrast, instead of analysing the whole of the original data. Now, I've also got a new procedure, VAS means, that will save those means and the other information that you need from an analysis by VA series. And you'll know that VA series is one of the procedures that underwrites the automatic REML menus that we have. This is a script that will do the analysis, but I'll show you that using the menu. I'm going to run that in GenStat. We've got the data set in a spreadsheet wheattrials.gsh. You can see we've got a trial factor representing the different experiments. Entry is the set of means that we want to estimate or use in the meta-analysis. We've got a plot factor, which we're not going to use, but we've also got row and column factors, which we're going to use in order to fit a spatial covariance model. And we've got a block factor. What I'm going to do is to analyze that using the menu for automatic analysis of a series of trials. And you can see the Y-variate is yield, experiment factor is trial. We've got a block factor, block. Row and column factors are going to be used for the spatial model, and the fixed model is entry. If you look at the options, you can see that I've said I don't want to run a meta-analysis. We're going to use the new menu instead. I'm not going to display any output from the individual trials other than the candidate models, but we're going to see a summary at the end and we're going to see the best model printed for each of those individual trials. We're using the menu to analyze each of the trials and automatically find the best random model using the Bayesian-Schwarz information coefficient. We're using the FAST strategy for that. You can see that we're going to fit a spatial correlation model only if the plots are in a regular grid, but we're going to estimate missing data values because there are some missing plots here in order to have a regular grid for some of the trials. Otherwise, it's just the usual stuff. We're constraining the variance components to be positive, we're estimating the constant term, and so on. I'll click on Run, and you can see that the analysis takes place. Here we have the best model for each of those experiments. Now, the menu doesn't currently allow you to save the entry by trial table of means, so I'll have to revert to the script for that. It's the one you've seen on the slide. And you can see we've got a call to the new VAS means procedure. The factor is entry, so we're going to form trial by entry means, saving the means in a table called means. And we're also going to save average standard errors of differences. Those will be in a table classified by trial. Now, for the menu using vmeta, we actually need those in variates. So I can use the vtable procedure to put the means into a variate trial means and the average SEDs into a variate called trial SEDs. I'm saving the classification set for trial means, in other words, the new entry and trial factors. And just to make everything more readable, I'm going to duplicate those two factors and put them in two new factors, entry without a capital E and trial without a capital T, because that just makes it easier to read the results of the meta-analysis. So I need to run that script in order to have the information that I need, and then I can use the new menu. So let's run the script. Okay, you can see we now have saved those various tables and converted them to variates as required. I'll minimize these menus to make life easier. Okay, I can now open the meta-analysis menu, and the one I want is this new one, multi-treatment meta-analysis of summaries. I've already filled it in here to save time. You can see that the means are in this variate trial means that we constructed using vtable. And then we've got the new factor entry for our treatments and the new factor trial for the experiments. We're supplying the average standard errors of differences of means. So we've got this radio button checked, and I've entered trial SEDs as the variate that we're going to use for that. If we look at the options, we can select the type of output that we want. I'm just going to have the model variance components and the treatment means and the covariance models. But I need to say what sort of variance structure I want over the experiments. And here I'm selecting diagonal matrix. In other words, I'm going to have a different residual variance for each of the trials, but no correlations between the trials. So click on OK, and I can click on Run, and the meta-analysis takes place. And as you see, it's much faster than analyzing the whole of the data. If you want to have a faster result, or if you can't make the analysis of all the data work, this is the one to use. So you can see I've got the estimated parameters for the covariance models. The off-diagonal elements are bound because we've got the full matrix here. We're just estimating a variance within each of the trials. And then we've got the predicted means combined over all the sites. So that's what we have new in meta-analysis. Next, I'm going to look at the new facilities we have to explore REML fixed models. The fixed model has perhaps been of less interest to people using REML than the random model because REML arose from variety trials and there you're often interested in getting BLUPs. So the fixed model perhaps hasn't had the attention that it deserves, and we've attempted to put that right in the 21st edition. We've added a new menu using a new procedure v all subsets to look at all subsets of the fixed terms, and we also have a new menu and procedures, VRAD, VRDisplay and so forth, to add, drop and try terms from the fixed model, just in the same way as you would with the directives add, drop, fit, switch and try in ordinary regression. These work by using a generalized regression analysis with a weight matrix that's based on the variance components from the original REML analysis. In other words, the analysis with the full fixed model. Now, because we're using common estimates of the variance components for all of this, it means we can use the Akaichi and Schwarz-Bayesian information coefficients within all subsets, just as we would in ordinary regression. When we're using the procedures to add, drop and try terms, we can use the residual mean squares of the current model to assess each change as we would in ordinary regression. But also, as we're using a weighted analysis, the residual mean square from the full model, putting the full fixed model, will be 1. And so it's easy to use that residual mean square for all of the terms, in other words, to assess them all with the same measure of random variation, just as we would if we were looking at an analysis of variance table. Given that I come from analysis of variance as my initial specialization within GenStat, I find that particularly attractive. In contrast with the usual method that you might use to look at the fixed model, where you change it by dropping or adding terms in a sequence of V components commands, the fixed terms that you're not fitting will be included in the random variation, and that's going to vary from fit to fit, just as it does if you use the add, drop, switch and try in ordinary regression. Now, because it's varying from fit to fit, I think that can make it quite difficult to reach clear and consistent conclusions. My preference would be to do it the ANOVA way, but of course you have the opportunity to make your own mind up on this. But just as a footnote, we do now provide AIC and SBIC calculated from the full likelihood, as suggested by Ari Verbler's paper last year in the Australia and New Zealand Journal of Statistics. So you can use AIC and BIC with the full likelihood if you want to use those to assess fixed models in an ordinary REML analysis. Just as a footnote, the 20th edition we had screening tests with the fixed model, but not any of these other facilities that I hope you'll find useful. I'm going to demonstrate those using a set of data that I looked at also at Queenstown, and this is from a paper that I had with John Quinn when he was at the University of Oxford, studying the responsiveness of great tits, that's Parus major, to the risks of starvation and predation. And the idea is that you want to look at how individual birds balance the risks of predation, and we can assess that by having feeders in exposed, in other words in dangerous positions, or in sheltered, safer positions, and starvation. In the morning it's more important to feed because the birds will be very hungry after a night than it is in the afternoon. So the starvation chances are going to be higher in the morning than the afternoon. We're going to relate that to their personality, which John and his colleagues assessed by looking at some of these birds in the laboratory. And that's what we call the behavioural plasticity. The full fixed model then has 4 factors: risk, that's the position of the feeder, crossed with AM/PM, time of day, and that's going to assess the starvation aspect, and then the age of the birds and their gender. The full random model has the individual birds and location, the location being 8 independent sites in Wytham Wood near Oxford, and the 3-way effects of bird risk and AM/PM, but of course the terms that are in the fixed model will be removed automatically from the random model by REML, so that's just a short way of saying bird with its risk and AM/PM within bird. The Y-variate is the logit of the percent time at the low starvation risk feeder. Well, at Queenstown, I looked at forming the random model using this script, and I'm going to use that again this time because we're looking at the fixed model. That's our interest this time. So I will just run that again in order to verify that the best model, according to the Akaichi information coefficient that I used at Queenstown, is indeed bird plus location plus bird.location, bird.risk, and bird.risk.AMPM. And to save time, I've run that already within GenStat. You can see I've loaded the data and run exactly the script that you had on the slide. And we've got now our best random model, which we can use in the REML menu. I'll minimize this window and then we can look at the REML menu here. So fixed model, that's the full fixed model. The random model is the one that we've decided to use based on the AIC. I can run that and you can see we get the standard output with the walled tests. If I want to now use the new facilities, I can click on Explore Fixed Model, and you can see we get this menu here where we've got all the available fixed terms. Can't drop any because we haven't moved any across into the current model yet. We can try terms, we can fit the full model, we can return to the null model, and so on. I'm going to start by fitting the full model. Okay, you can see here's the output. We've got the standard regression accumulated analysis of variance. That's going to be helpful for me because it'll give me an idea of the batting order in which I might want to try or drop terms. I won't run through all of this because we're limited in the time for the presentation, but let's just look at how we might explore the model. I can highlight the four-way interaction here, and I can click on try to find out the effect of dropping it from the model. In fact, I could see that from the accumulated ANOVA, but this is just to show you how it works. So we've got the change here, and we've got the residual of the initial model, in other words, the one I had before making that change. And here, that's the full model, so you can see the residual mean square is 1. And if you look at the mean square for this four-way interaction, you can see there's really no evidence to hold it in the model. So I can drop it. You can see it's still highlighted here. Click on drop, and you can see that now moves into the available terms window because it's available to add back, and the model has now changed. In fact, I'm still printing the accumulated ANOVA. If I wanted to do this in real life, I probably wouldn't want to keep that appearing on the screen. So you can use these facilities to explore the model. I won't do that now, but I think that gives you an idea of how it can be done. But I'll return to the slides. You can see I've fitted the full model, and you get the accumulated analysis to guide your next steps. And then I can drop the terms as in the analysis in the paper. I can try the four-way interaction. As you saw, you get the output here, and then I can drop it. So we can continue with that until we reach a conclusion. This is actually what the conclusion will be. These are the only terms that we need actually within this model. These give me, in fact, the same model as I had within the paper. Now, in the output here, the standard errors will be based upon those variance components that we estimated in the full fixed model. And again, with my ANOVA background, that would actually be what I would prefer. So what I would tend to do is return to the REML menu and then form some predictions with just these terms that seem to be important based upon the variance estimates from fitting the full fixed model. But if you don't want to do that, you can click on Export Current Model to Menu and Close, and then REML will refit the analysis with just those terms that we have in that current model. So you could remove those other ones and put them into the residual if that's what you want to do, or put them into the random model if that's what you want to do. I won't run the all subsets live, but I will show you how you can do it. If I now go back to the REML menu and I go to further output, you can see I've now got the all subsets menu. I can run that now to verify, if you like, that the conclusions we came to are the right ones. All subsets tended to be disapproved of by statisticians in the past because you could end up with all sorts of spurious ones. I find it useful to check my conclusions when I've fitted a model by hand because it may be that the sequence that I chose has taken me down a blind alley. So if I do that with the data here, I'll return to the slides and just show you the results. You can see that I end up with set 56. See, there were 332 sets altogether. Set 56 is the best according to AIC, and that is indeed the one that we came up with from the exploration of the fixed model. Another important focus of the 21st edition is to provide encouragement for you to use the commands. Now, the ability to use commands as well as menus has always been a strong point of GenStat, but I think we perhaps haven't promoted that as much as we could have done. So independently of the GenStat release, we'll have a new course on commands, programs and procedures that you can study online. We have a new directive syntax and a procedure SP syntax that you can use to access details of the syntax. Here's an example. We're using SP syntax here to access the syntax of ABLUPS. So SP syntax calls the syntax directive to get the details and then loads them into a spreadsheet where you can study them more easily. You may not find that particularly important, but what I hope you will find helpful is that SP syntax and syntax are now used by the client to implement a new menu for writing commands. We also have new menus for inserting pre-prepared code into text windows that I'll show you after I've demonstrated the ability to write the commands. Well, I'll look at that within GenStat. Here I've rerun the split plot analysis of the OATS dataset because I'm going to use the results from that in a moment after I've written a command. So to write a command, first of all, I need to open a text window in which I'm going to place the command once it's been written. And once I have a text window as the current window within the client, I can go to the Edit menu and click on Insert Command and get this menu that allows me to select which command I want to build. And I can search the details of the commands either by name only, and I can do the name from the start, or you could look actually within those descriptions. Here I'm searching by the name from the start, so if I type ABLUPS, you can see I get the line for the ABLUPS procedure, its name, and the little short description of what it does. Click on Build Command, and up comes the menu. You can see I've got a tab for the parameters and a tab for the options. So as I've already done this split plot analysis, you can see I have got some terms for which I might print the blups. So I'll enter blocks here, and I'll look at the whole plots as well. So I'll put in a slash and then I'll put in W plots. If you look at the options, you can see we've got a print option and we've got one to say which terms we want to print. That would override the parameter. The parameter specifies the ones that we might want to print or save the information. And I can say what sort of standard errors I want, the default being differences and blups. And I'll leave those defaults. Just click on OK. And you can see I've now got the command written into my text window. So to run that, I can put the cursor into that line, go to the Run menu on the menu bar, and click on Submit Line. There we are. You can see it's printed the blups together with their standard error and standard error differences. The next thing I want to show you is how you can insert sections of code into your text window. And again, this comes off the Edit menu, provided you've got a text window open, and we select the Insert Code option there. So let's go back into GenStat and do that. I'll bring the text window up, go into the Edit menu, and you can see I've now got the ability to insert code. This is an alternative way of going back to building a command, or I can look at the various code sections that are available and either edit or insert them, or the ones that are available come up in this menu here. But let's look at the Edit Insert Code Sections one. You can see we've got a whole range of possibilities. The standard for loop with n times and an index, or for with a dummy. We've got if then, if else, or if else, and so on. This provides a very convenient way, I think, of putting in standard templates for things you might want in your program. The nice thing about it is that you can add your own ones. You can add new, you can save them to a file if you want to share them with your colleagues, or you can load them from a file if you want to use ones that your colleagues have written and are willing to make available to you. So to show this in action, you can see I've got the for n times bit here, and if I click on Insert, it gets put into my text window, and then I can continue to fill in the contents of the for loop and so on. So I think this provides a way of perhaps making it easier for you to write programs. And if you have something that's useful, please share them with us and we might add that to the released version too. So you can see this is what we've achieved within the menu. We have our input window with that little template there. Now, another important aspect of syntax is that it can access the source code of procedures. For example, if you wanted the source code of ablups, you can execute the line syntax, ablups, and save the source and then print it. This isn't really necessary for library procedures because, as you may know, you can use the procedure source option of the help menu. But I think it is particularly useful for those people who have old procedure libraries that they're still using where they no longer have the original program that created them. And we have these come through on support from time to time where people want to change those procedures, but they can't find them anywhere in their files. So we can now recover those procedures and send them back to you or to modify or modify them for you. In the next release, we'll have an automatic system for reformatting those procedures or any other source code that you might like, but that's something that's in the future. So we reach a conclusion. And of course, if you want more details about what's in GenStat, the full documentation, as always, is available online. You can see here the GenStat guides that you can get from the help menu. And we now have these online courses being developed. But the most important take-home message, I think, is to make sure that your organization does update your copy of GenStat so that you can take advantage of the changes. We do know that there are some organizations where people are still using out-of-date copies, and that's a shame because we work hard to make GenStat include lots of useful new facilities, and we really do want you to use them. That's one take-home message. The other one is to please let us have your feedback about what you like or don't like or would like, and that'll help us plan the 22nd edition next year. So GenStat's life goes on in these difficult times. Please keep safe until COVID-19 is less of a danger so that we can meet again in 2022.